Hey, sixth graders. Today you're going to do some notes on scientific tools and measurement. And as you do your notes, I want you to, or as you watch this video, I want you to fill in your notes sheet that is green. Our objective is I can describe the different tools and units of measurement used in scientific investigations. And the essential question is, what are the tools and units used in science? Remember, that's the question that we want to be able to answer at the end of this. Here's our vocabulary for the lesson. So you can pause here and copy this down into the top part of your notes. I'll read through them for you. Measurement is a description that includes a number and a unit. Accuracy is a description of how close a measurement is to the true value of the quantity measured. Precision is the exactness of a measurement. SI units are the modern metric system that is the measurement system used for all scientific measurements. And scientific notation is a short way of representing very large or very small numbers. Let's watch a quick video on the metric system.
What does the French Revolution have to do with the time NASA accidentally crashed a $200 million orbiter into the surface of Mars? Actually, everything. That crash happened due to an error in converting between two measurement systems, US customary units and their SI or metric equivalents. So what's the connection to the French Revolution? Let's explain. For the majority of recorded human history, units like the weight of a grain or the length of a hand weren't exact and varied from place to place. And different regions didn't just use varying measurements, they had completely different number systems as well. By the late Middle Ages, the Hindu-Arabic decimal system mostly replaced Roman numerals and fractions in Europe. But efforts by scholars like John Wilkins to promote standard decimal-based measures were less successful. With 250,000 different units in France alone, any widespread change would require massive disruption. And in 1789, that disruption came. The leaders of the French Revolution didn't just overthrow the monarchy. They sought to completely transform society according to the rational principles of the Enlightenment. When the new government took power, the Academy of Sciences convened to reform the system of measurements. Old standards based on arbitrary authority or local traditions were replaced with mathematical and natural relationships. For example, the meter, from the Greek word for measure, was defined as 1/10,000,000th between the equator and North Pole. And the new metric system was, in the words of the Marquis de Condorcet, for all people, for all time. Standardizing measurements had political advantages for the revolutionaries as well. Nobles could no longer manipulate local units to extract more rent from commoners, while the government could collect taxes more efficiently. And switching to a new republican calendar with 10-day weeks reduced church power by eliminating Sundays. Adoption of this new system wasn't easy. In fact, it was a bit of a mess. At first, people used new units alongside old ones, and the republican calendar was eventually abandoned. When Napoleon Bonaparte took power, he allowed small businesses to use traditional measurements, redefined in metric terms. But the metric system remained standard for formal use, and it spread across the continent along with France's borders. While Napoleon's empire lasted 8 years, its legacy endured far longer. Some European countries reverted to old measurements upon independence. Others realized the value of standardization in an age of international trade. After Portugal and the Netherlands switched to metric voluntarily, other nations followed, with colonial empires spreading the system around the world. As France's main rival, Britain had resisted revolutionary ideas and retained its traditional units. But over the next 2 centuries, the British Empire slowly transitioned, first approving the metric system as an optional alternative before gradually making it official. However, this switch came too late for 13 former colonies that had already gained independence. The the United States of America stuck with the English units of its colonial past, and today remains one of only 3 countries which haven't fully embraced the metric system. Despite constant initiatives for metrication, many Americans consider units like feet and pounds more intuitive. And ironically, some regard the once revolutionary metric system as a symbol of global conformity. Nevertheless, the metric system is almost universally used in science and medicine, and it continues to evolve according to its original principles. For a long time, standard units were actually defined by carefully maintained physical prototypes. But thanks to improving technology and precision, these objects with limited access and unreliable longevity are now being replaced with standards based on universal constants, like the speed of light. Consistent measurements are such an integral part of our daily lives that it's hard to appreciate what a major accomplishment for humanity they've been. And just as it arose from a political revolution, the metric system remains crucial for the scientific revolutions to come.
All right. So that gave a little bit of background on how the metric system came to be, and that every place in the world uses a metric system except the United States and a few other countries. And that's why we use it in science class. All right. We're on to the tools that we will use. The first one is the meter stick or ruler, and we use this to measure length. The measurement unit that we use is meters. Okay. You'll have access to the slideshow to look at how to use a ruler and then have some practice once you are finished with these notes. The second tool we will use is a triple beam balance. We use this to measure mass, and it's measured in kilograms or grams. A stopwatch is used to measure time, and we use seconds in the metric system. A thermometer is used to measure temperature, and we measure in degrees Kelvin. However, we often use Celsius as well in science class. The graduated cylinder or beaker is used to measure volume. It's measured in cubic centimeters or liters. A spring scale is used to measure weight, and we use that to measure newtons. And we have one more video on accuracy versus precision.
As the story goes, the legendary marksman William Tell was forced into a cruel challenge by a corrupt lord. William's son was to be executed unless William could shoot an apple off his head. William succeeded, but let's imagine 2 variations on the tale. In the first variation, the Lord hires a bandit to steal William's trusty crossbow, so he is forced to borrow an inferior one from a peasant. However, the borrowed crossbow isn't adjusted perfectly, and William finds that his practice shots cluster in a tight spread beneath the bullseye. Fortunately, he has time to correct for it before it's too late. Variation 2. William begins to doubt his skills in the long hours before the challenge, and his hand develops a tremor. His practice shots still cluster around the apple, but in a random pattern. Occasionally, he hits the apple, but with the wobble, there is no guarantee of a bullseye. He must settle his nervous hand and restore the certainty in his aim to save his son. At the heart of these variations are 2 terms often used interchangeably: accuracy and precision. The distinction between the two is actually critical for many scientific endeavors. Accuracy involves how close you come to the correct result. Your accuracy improves with tools that are calibrated correctly and that you're well trained on. Precision, on the other hand, is how consistently you can get that result using the same method. Your precision improves with more finely incremented tools that require less estimation. The story of the stolen crossbow was one of precision without accuracy. William got the same wrong result each time he fired. The variation with the shaky hand was one of accuracy without precision. William's bolts clustered around the correct result, but without certainty of a bullseye for any given shot. You can probably get away with low accuracy or low precision in everyday tasks, but engineers and researchers often require accuracy on microscopic levels with a high certainty of being right every time. Factories and labs increase precision through better equipment and more detailed procedures. These improvements can be expensive, so managers must decide what the acceptable uncertainty for each project is. However, investments in precision can take us beyond what was previously possible, even as far as Mars. It may surprise you that NASA does not know exactly where their probes are going to touch down on another planet. Predicting where they will land requires extensive calculations, fed by measurements that don't always have a precise answer. How does the Martian atmosphere's density change at different elevations? What angle will the probe hit the atmosphere at? What will be the speed of the probe upon entry? Computer simulators run thousands of different landing scenarios, mixing and matching values for all of the variables. Weighing all the possibilities, the computer spits out the potential area of impact in the form of a landing ellipse. In 1976, the landing ellipse for the Mars Viking lander was 62 by 174 miles, nearly the area of New Jersey. With such a limitation, NASA had to ignore many interesting but risky landing areas. Since then, new information about the Martian atmosphere, improved spacecraft technology, and more powerful computer simulations have drastically reduced uncertainty. In 2012, the landing ellipse for the Curiosity lander was only 4 miles wide by 12 miles long, an area more than 200 times smaller than Viking's. This allowed NASA to target a specific spot in Gale Crater, a previously unlandable area of high scientific interest. While we ultimately strive for accuracy, precision reflects our certainty of reliably achieving it. With these two principles in mind, we can shoot for the stars and be confident of hitting them every time.
All right, so that's looking at the difference between precision and accuracy. So, some examples of that. So, high precision is going to mean that all of the shots that you do or all of your trials, you get a similar answer, even though they might not be accurate. It might not be exactly where you want it to be. So, for example, this first picture of the bullseye, you want to be in the middle at the bullseye. So, the accuracy is low, but it's precise. You keep hitting at the same spot. The second picture is both high precision and high accuracy because they're hitting it in the middle and all of the time. This one is high accuracy, this third one, because they're all pretty close to the middle, but low precision. They are not, the numbers are not close together. And this last one is low precision and low accuracy. They're not in the middle, so it's not accurate. And they're not really that close together, so they're not precise.